Okay, so we can begin. Today we're supposed to look at order of a group. We began looking at groups the other time. So we want to know what is the order of, when we talk of order of a group, what do we mean? Okay, the order of a group means the number of elements in that group. That's what we mean by the order of a group. Now we talked of two types of groups that we have, two types of groups. We have the additive group and the multiplicative group. Now, an example of an additive group is the group of integers mod n, a group of integers mod n, which we write this way. This is an example of an additive group. So then the question is, how many elements does this cell group has? So this group has n elements, n elements. So if we have a group of integers mod n, the number of elements in the group is n. So in fact, this is the group comprising of elements 0, 1, 2, all the way up to n minus 1. So when you count these elements, you'll find there are n of them. So for instance, if we have Z8, Z7, is a group of integers mod 7. So it has 7 elements, and the 7 elements are 0, 1, 2, 3, 4, 5, and then 6. These are the 7 elements in this group. So if anybody writes for you this, then you must know that this is an additive group with 35 elements. So the order of this group is therefore 35. So this is how we denote the order. So if somebody writes this, this means the order of this group. So the vertical lines mean is a command to find the order. So I can say the order of this group is n, or the order of this group is 35. So that is how we denote the order of a group. So that is for the additive group. And what about the multiplicative group? And if it's a set of integers mod n, we say that if it's a multiplicative group, we just, this is how we denote it. This is how we denote it as a set of integers mod n star. Now we said for this to be a group, we said that the elements here should be those which are relatively prime, smaller than n and relatively prime to n. Those are the elements. Those are the elements here. So it will be 1 and any other elements relatively prime to n. So for instance, if we are talking about Z7 star, that's a prime number. But of course, the elements of the group will be those which are relatively prime to 7. So that if somebody writes for you Z star 7, then this group has the elements as 1, 2, 3, 4, 5, 6, and 7. These are relatively prime to, no, 7 is not there. Up to 6. These are relatively prime to 7. So if somebody writes for you Z8 with a star, Z8 with a star, these are integers mod 8. Then these will be elements relatively prime to 8. And how many are they? They are which ones are 1, 3, 5, and then 7. These are the elements which are relatively prime to 8. There are 4 of them. 4 of them there. Now, so the order of Z star 8, the order of Z star 8, therefore, the order of this group therefore, is 1, 2, 3, 4. The order of that is 4. So that is how we tell the order of a group. But of course, when n is prime, okay, for the additive group, there's no problem. For the additive group, there's no problem. The order will be just equal to n. The order will be equal to n. So because we've said, for instance, Z8 would have 8 elements. Z8 will have 8 elements. So if it's an additive group, there's no problem with the order. You just look at the value of n, and that is the order. But if it is a multiplicative group like this, the one with a star, if it's that, the one we are talking about, and it's a multiplicative group, and then there are a few things we have to look at for us to tell what the order is. One, we've said the elements of this group should be those which are relatively prime to n. Those are which are relatively prime to n. Now, if n is prime, if n is a prime number, for instance, this 7 is a prime number, the order will be p minus 1. So that means if I'm given Z19 with a star, and I'm asked to find the order of this group, I'll just take 19 minus 1, and I know that it has 18 elements. It has 18 elements. So if I'm given Z star 17, and I know that 17 is a prime number, then I know that the order of this group has 16 elements. Has 16 elements. So if it's prime number, and then you just take that prime number minus 1. But if the number is not prime, then we shall use what we call the Euler phi. The Euler phi of n will give us the number of elements. The Euler phi of n. So I've defined what the Euler phi of n is, the Euler phi function. And I've said the Euler phi function, by definition, is just the elements which are smaller than n and are relatively prime to n. Elements which are smaller than n, positive elements which are they're positive. They must be positive. They should be greater than 0. That's what it means. They should be greater than 0, but less than n, and are relatively to n. That's what we call the Euler phi. And you see, that is what we've talked about. Those are the elements of Z star. Z star n. We said these are elements which are relatively prime to n and are smaller than n and are positive. So when you talk of Z star 8, no star 8, these are elements which are relatively prime to 8. These are elements which are relatively prime to 8. So this is the Euler phi of 8. Euler phi of 8 is 4. Euler phi of 8 is 4. And that is, I've given a small table here. When n is 8, when n is 8, the Euler phi is 4. When n is 9, the Euler phi of 9 is 6. When n is 1, the Euler phi is that. So what is now interesting is how do we calculate the Euler phi of n, Euler phi of a number? I've already said that if the number is prime, then to get the Euler phi, you just subtract 1 from that number. And that is what you are seeing from this table. That if S7 is prime, so that means the Euler phi of 7 is just 7 minus 1, which is 6. Another number that is prime here, 5 is prime. So you can see the Euler phi of 5 is just 5 minus 1, which is 4. And we have, of course, you don't need to memorize this. You must know what it means. The Euler phi of 5 is the number of elements which are less than 5 they are greater than 0 and are relatively prime to 5. In other words, what we mean by relatively prime, for those who are joining us for the first time, we say that two numbers A and B are relatively prime if their GCD is 1. If their GCD is 1, or if the only common factor between these two numbers is 1. For instance, 1 and 5 are relatively prime because the only common factor is 1. 2 and 5 are relatively prime. 3 and 5 are relatively prime because the only common factor between them is 1. 7 and 9 are relatively prime. Their only common factor is 1. That's what we mean by relatively prime. 10 and 13 are relatively prime. Their only common factor is 1. So what we are saying, when we talk of Euler phi of n, we are asking which numbers are relatively prime to n. That's what we mean. When we talk of Euler phi of 7, we are asking ourselves, how many numbers are relatively prime to 7 and are less than 7 and are positive. So, for instance, when we talk of 10, the Euler phi of 10, we're asking ourselves, how many numbers are relatively prime to 10 and are smaller than 10? Those numbers are 1, 3, 4 is not, 5 is not, 6 is not, 7 is, 8 is not, 9 is. So 1, 2, 3, 1, 2 is not, 3 is, 4 is not, 5 is not, 6. So there are 4. There are 4 numbers which are relatively prime to 10. Now, I've told you that if n is p is prime, then we just take p minus 1. But if it's not prime, then you must find out what are the factors of that number. For instance, what are the factors of 10? The factors of 10 are 2 and 5. Since the factors of 10 are 2 and 5, for you to get the Euler phi of 10, you take 1 minus a half. This a half, this 2 is coming from this. The 2 on this a half is coming from this. Then times 1 minus 1 out of 5. That 5 is this 5. Then multiply by the 10, the number that we are finding the Euler phi for. It had only 2 factors, and that's why you're seeing the 2 factors are here. Those 2 factors are here. So this gives you, the first bracket is a half, the second bracket is 4 out of 5, and then there's a 10, and the answer is 4. The answer for that calculation is 4. So that is if n is not prime, and that is the formula I've given here. That is the formula I've given here, where P1, P2, P3, all the way up to Pk are the prime factors of n, the prime factors of n. So I want to take this example. Example is find the order of this group. Find the order of this group. Now this one is there's supposed to be a star here. I forgot a star here. Supposed to be a star there. The group is without is the star there. Because if the star was not there, then it would have been easier just to tell the order. The order would be equal to n. The order of that would be equal to n. So this one has a star. So if it has a star, and you are asking about the order of this group, so the solution that we have is that the order of this group with a star there, 400, is equal to the Euler phi of 4900. Euler phi of 4900. So they are the same. The out of this group is the same as the Euler phi of that. And since it has a star, the Euler phi of course is given by, this one is not a prime number. This is not a prime number. So we find out what are the factors of this number. So the first factor is 2. Let me just find out using my calculator how many times it will go there. Because I want to find all the factors. 4900 divided by 2. Divided by 2. It goes there 2,450 times. Then another factor is 2, which goes there 1,225 times. Then another factor here, 3 is zinc. This is 3 plus that is 5. 3 is not a factor. 3 is not a factor because the sum of these numbers is 10. 3 cannot divide it 10. So 5 is a factor. 5 how many times? 245 times. And then 5 again is a factor. How many times? 49 times. 7 is a factor. How many times? 7. And 7 is another factor. So how many factors do we have? The factors we have, that we have here, I'm not talking about prime factorization. I'm just asking how many numbers can divide this number? Which numbers can divide this number? So the numbers which can divide this number, one of them is 2, and the other number can divide it is 5, and the other number that can divide it is 7. So these are the factors. So of course, I'm not talking about prime factorization. We know what that means. Factorization is writing a number in terms of its prime factors. But what we're interested in, which numbers can divide this number? So we've discovered that so using our formula, then the Euler phi of 4900 be the same as 1 minus a half, and you know where the 2 is coming from? 2 is coming from these factors. And then 1 minus 1 out of is coming from factors, and times 1 minus out of 7, then again is from these factors, then times the number that we finding prime the Euler phi. The first bracket is a half. The second bracket is 4 out of 5. This other bracket is 6 out of 7. Then multiply by that. When you do that, you get 1,680. So that becomes the order of that group. So when we talk of the order of a group, we need to know what it means. Is the number of elements in that group. So it means this group has these elements. Of course, you can be asked to list those elements. You can be asked to list, and we know how to list these elements. So we just list 1. We are listing numbers which are relatively prime to this, and the other number that cannot divide this number, that has no common factor with this number, should be 3, and so on. Of course, we have Rust program that can generate all the prime numbers here. But that one I'll show you later. What I'm interested in is the Rust program that can give us Euler phi. That's what I'm interested in. Then next time I'll give you a Rust program that can give us orders of groups and so on. How you get it? You get it. Example is find Euler phi or find. The question is find so groups. This groups. So the first group saying 10 has 8 is mod 840, and the other group is mod 930. All of them are multiplicative groups. 19 is a prime number, so finding the the order of that group is very easy. Just subtract 19 and you get 8 is not prime. So find numbers which you can divide 840 are 2, 3, 5, and 7. Prime numbers, not just numbers. Prime numbers can divide 840. Prime numbers can divide 8 are 2, 3, 5, and 7. Of course, you know how I got a half. I got a total of 3. How I got a half, I just took 1 minus a half. Then this other one, I took 1 minus a third. This other one, I took 1 minus a quarter. And then now a fifth. And this other one was 1 minus 1 out of 7. And then multiply by 840. The same thing for this. You get this to be the Euler phi, or the orders of those elements. Now, so I told you that today I'll show you Rust program, how to write Rust program of calculating the Euler phi. There are 2 ways of doing that. There are 2 ways of writing Rust program that calculates Euler phi. I'll show you the 2 ways. Of course, there could be other ways. Since you are builders, you can come up with other ways of doing that. Now, the first way of writing the Euler phi is what we just explained in this calculation. What we've just talked about in this calculation. The first way I'll be showing you is where, first of all, we must understand what we mean by Euler phi. We must understand what it is. Let me just go back to what we mean by Euler phi of n, so that we now think of how do we write a program for Euler phi, a program that can give us the number of elements relatively prime to n, so that if we ask to find Euler phi of 840, tell it and 2 elements. Now, so therefore, you have n. Let me say n is 8. That is our example. I'm just taking that example. I want to assume it's 8, and I want to write a program to give me the number of elements which are relatively prime to that. So the first thing I know is that the numbers I'm supposed to write are numbers between 1 all the way up to 7. Those are the numbers. So some of these numbers are the ones that are relatively prime to this. So for me to write this program, therefore, 1, I should have the GCD function. What the GCD function will be doing will be checking from 1 up to 7, check each of these elements, find the GCD, for instance, of 1 and 8. If it finds that this GCD is 1, then it stores 1 somewhere, because 1 is one of the numbers I'm looking for, which are relatively prime. Then it goes to check 2 and 8, find the GCD. So it will be using the extended Euclidean algorithm to find this GCD, or the Euclid's algorithm. Now, if it finds that this is 2, then it does not qualify to be relatively prime. So it does not qualify to be relatively prime. So it will again go to the next number, find the GCD of 3 and 8. And if it finds that this is 1, and again, it stores it somewhere there where it was storing the others. So it had initially the vector was empty. The vector was empty. So when we did this, we pushed 1 inside the vector. Then we came to 3. There, it was not relatively prime. And then we came, no, 2, it was not relatively prime. It comes and does a GCD of 3 and 8. So again, we push another element there, which is 3. it proceeds to 4, has a GCD of 4 and 8, and this is not equal to 1. So there's nothing to push in that vector. That is what it does. So you must have that function. That function will be testing all the elements. For instance, when you're talking about 840, we want to find elements which are relatively prime to 840. How many are they? So what it will be doing, it will be checking elements all the way from 1 all the way up to 39, checking each one of them, combining with the 840 and finding the GCD. Combines with the 840 and finds the GCD, and it wants after that. So the GCD function is just doing that, just finding the GCDs. Then you need relatively prime function. Relatively prime function. So the relatively prime function will now come. These elements, GCD function had already found the GCDs. So the relatively prime function is just picking those which are relatively prime. So it just picks, for instance, in this case, it picks 3 because it has seen that the GCD of 3 and 8 is 1. It moves around again, picks 5 because it has seen the GCD of 5 and 8 is 1, and so on. So the relatively prime function is there, and its function is just to pick those elements which are relatively prime. But the GCD function had already done the GCDs. So the GCD function has already done the GCD. So this one is just now picking. When this one finds the GCD, it checks whether that is a relative prime, it picks it. This one does the GCD again, checks, and then picks it. Then you also need the main function. You also need the main function now to combine all those and give you the results. So that means you need, that is one way you can do that. And of course, I've said is not the only way. You can also do without this GCD function. And again, I'll show you how you can write without the GCD function so that you only have the relatively prime function. And the relatively prime function, again, can do all this work together and combine all this work together and do it without necessarily having to calculate the GCDs. So you can find without, like in this case, like look at it in the case in which we've done these examples. The case in which we've done these examples to find how many relatively prime numbers are here, we did not find the GCD. We did not find. So we can also create a relatively prime function, Rust function, just to work the way these examples have worked. Just to work the way these examples are without go through finding the GCD and checking it's relatively prime. But of course, that is another way. Check which of these numbers are relatively prime. So my first Rust program is the first example I talked about, the first where I have the GCD function, and then I have the relatively prime function, the Euler-Phi function, and then I have the main function. So the GCD function is doing the GCD. And look at what it's saying. Now, first of all, this is where you input the numbers. So you input here, this is the main function, and the main function will call on the relatively prime function. We'll call on the relatively prime function, and the relatively prime function, of course, will call on the GCD. So the GCD does it. The GCD begins, and if supposing you had a number 5 and a number 0, so where A, B is 0, the GCD function is saying that if B is 0, if one of the numbers is 0, then the number that is not 0 becomes the GCD. Becomes the GCD. Else, that means in cases where none of the numbers is 0, then the GCD function calls itself with B and the remainder of A on division by B. So it calls itself. So that is where none of the numbers is 0. Then the GCD function calls itself with B and the remainder of A on division by B. So this is, of course, how we calculate the GCD. So it will be doing that to calculate the GCDs. Now, once it calculates the GCD, the Euler function takes over. And the Euler function begins by letting the rest, it lets, first of all, it lets the Euler phi of n be 0, but it's mutable. It's mutable. That means it will be changing. So it just begins by letting it be 0. But then this 0 will change to another number, change to another number, change to another number, and so on until we arrive at the number that is. So that means it begins with a 0. So then it will move from I1 to n, I1 to n, I1 to n. So it checks. For instance, if we had our n was 8, it will check if 1 is relatively prime to 8. Of course, it's using a result from above. It's using a result from above. That is what it's saying, GCD of n and I. So it moves from it moves with I from 1 to n, where I could be 1, could be 2, could be 3, all the way up to n. Then it checks for the GCD. If the GCD of this I and n is 1, it makes the first count. It makes the first count. So what was 0 now changes to 1. What was 0 changes to 1. And then it goes to the next I, which is 2. Then it checks 2 and 8, for instance. If the GCD is 1, it will make a count. If the GCD is not 1, it does not count. So that is why he's saying plus 1. So it's adding every time if there is a GCD is 1. Now it goes to 3. I is 3 now. I is 3. Then it checks the GCD of 3 and n. If it's 1, another count. So this 1 changes to 2. That's why he say that it will be mutable. So the result will be mutable, it will be changing. So it's counting. Then it goes until the final count. Until the final count. Now it stops there. Now this one calls on it. This one calls on it. And it wants to see what this count is. That count is what it prints here. Prints the Euler phi totient function. The phi of n is the count that is here. So that is how this function will be working. But of course, I told you that there's another way you can do it without including the GCD function. And again, I'll show you how that one works. So let me just show you how it runs. Okay, so here it is. I think you can see it. Are you able to see it? Chris, can you see it? Chris Gashua, Gashau. Can you see it?
Yes.
Okay. So it has begun with a function GCD And I've just defined the number A and B to be U128. That means 128 bits. And we are talking of only positive numbers. That is why I have U there. I have U because I'm only interested with the positive numbers. If I would have been interested with the negative numbers, it will have been I. But of course, you're talking about the Euler phi should be a number greater than zero and less than n. So we don't need the negative numbers here. So there's no need of I. So we just use U. So we have A should be U 128 type, and then B also U128 type. Then the result will be U128 type. So this is the result of the GCD. And then if B is 0, then the GCD will be 1, it will be A, if B is 0. But if B is not 0, then it calls on the GCD of B and the remainder of this. So I showed you how the GCD is calculated. It's normally this remainder until B becomes 0. Until B becomes 0. So when B becomes 0, then the GCD becomes A, just as it has said here. So that is again what is happening here. What is happening here, we reduce this until B becomes 0. So when B becomes 0, A becomes the GCD. And then we have this Euler phi function that will be picking and counting those which are relatively prime. And then we have the main function. The number that I've put is 4,900 and what is this? This is 4 million. Okay, 4,900,447. So let's try and run this. Let's try and run this and see what it gives us. Okay, the result is here. Says the Euler phi function of that number. So it means this number is what is this? Give us this. Oh yeah, this number is prime. This number is prime because it's prime because you can see that it has just subtracted 1 from the number. It has just subtracted 1 from the number and given us the result. So that number is prime. I don't know where then the bell is ringing from. Okay. Now, so let's look what, let's change this number to another one, just in case, and change, we had looked at which number, 840. We looked at 840 and we, which one am I looking at? Okay, look at, let me change this number to a number that is not prime, which is 4900, and run this. So run that. Gives us, we had gotten that 1680. 1680 is the value. Now, so I've used U128 so that I could handle bigger numbers. So you can increase these numbers. But if you find that U128 cannot handle some numbers, you can still change this to big unit as we've done in our previous lessons. You can change this to big unit, which can handle bigger numbers. Now, of course, I've explained how this program works, how the the program works. Try to break down, and I've already explained that. I've already said that the GCD function would check the first thing. If B is 0, and then it will return the GCD. And if B is not 0, then it will go through the recursive call and find the GCD. I'm wondering what is something. Is it on my side or which side? Okay, but I don't think it has a lot of impact. Now, so can you see what I'm sharing? You can see what I'm sharing, is that okay? George Kuria.
Yes, I
can you see what I'm sharing?
Yeah.
Okay, thank you. Now, we have the Euler tangent function, and it does what it does. I've already said it will begin by taking the Euler phi to be 0, and then it will, this is mutable, that is why it's mute. Let mute count, and then we'll be counting. To be changing from 0 goes to 1 and so on. So for each integer I, it will check if the GCD of n and I is 1. If the GCD of n and I is 1, then this 0 changes to 1. Then it goes to the next number again, checks. If it finds the GCD is 1, again, that one changes to another number. Okay, so this one I think we've already explained. Now, if we have a bigger number, I've already said we can use the bigger, the big unit, the integer, big integer. But I'd also from the start, I had also said that it's not always that somebody who writes this code should always have the 3 functions, that you have the GCD function, that you have the Euler phi function, and then you have the main function. You can omit the GCD function and just calculate the same way we did calculate our examples, earlier examples. And that is what I want to say. Now, I want to show with this example. So this example, there's one I'll be running. And this is my code. Now, this code, what you realize is that I don't have the GCD function. I have the Euler phi function. And the Euler phi function, I showed how it does calculate until gives you the result. Now, it has already said that. It has already said what it will be doing. Of course, these are the libraries. Now, this library is just to, the first one here is to deal with the bigger integers. So this first one will be dealing with bigger integers, and this other one is just to initialize so that it can deal with the 0 and 1, so that it can deal with the 0 and 1. And this other one is just to be converting a number from a string to a bigger unit. Just that conversion from a string to bigger unit. So that is what it should be doing. But now look at how the Euler function is working. The Euler function, we've put n. We want to assume our n is 8. And you are saying that this n will be mutating. It will be mutable. Be changing from 8 to another number, to another number, to another number. So it will be mutable. Now, That is what the Euler function does. Then it says, if this n is 1, then it should return this result as 1. So what that means is that if n is 1, then the Euler phi will be 1. That's what this part is saying. This part is saying 1 to get 1 as the, because that will be. Otherwise, if that is not yes, if n is not 1, then it has now to begin doing the calculation. So the calculation begins from here. If n is not 1, it says, let the result be n. That is our initial result. So if n is not 1, then we begin as the result of n is n. That's what it's saying. Let neutral will not be permanent. It will be changing from time to time. It will be changing. So that's what it means by n clone with this bracket there. Now, that is the first assumption. We've said if n is 1, we already have the result. It prints the result as 1. In cases where n is not 1, let's say n is 8, then we begin by letting our result be 8. But then it will be changing. It's mutable. Then we let a number which is prime, mutable, and again this prime number will be mutable, be 2. So of course, that what this means is that the prime number we begin with is 2, and then we said from. So that means it's 2, we'll change to 3. We're only considering prime numbers. Only considering prime numbers. So 2, then 3, then 5, that's why we say mutable. P will be mutable. So let me say, for instance, our n is 8. Let me assume our n is 8. So that means our result, therefore, for the Euler phi of 8 is mutable 8. So it will be mutable, but we initialize it at 8. And then the prime number which can divide, the prime number, we let the prime number, our initial prime number we are going to check is 2. Now, these are just the initial conditions. Now our working begins with this loop. The loop says that if this p times p, if the square of p is less than or equal to n, if the square of p is less than or equal to n, then we enter inside the loop. If it's less than or equal to n, then we enter inside the loop. That means if it's not less than or equal to, if it's greater than n, there's no need of going inside the loop. Yes? This is p times p. If p times p, this means less than or equal to. If p times p is less than or equal to n, then we enter the loop and do what is inside the loop. But when we discover that p square is not less than or equal to n, then there's no need of going inside the loop. Let us assume, in this case, you have 2. 2 times 2 is 4, and the true is less than or equal to n. It's less than or equal to n. So we are to go inside the loop. Now, if we go inside the loop, we meet another condition, another loop here. There's another loop inside, if. And if says that if n divided by b gives you 0 as the remainder, if n divided by b gives you 0 as the remainder, you again enter a loop. You again enter another loop. That means cases where n divided by p does not give a remainder of 0, you don't now proceed in this loop. You don't go there. You only go in by p will give you a remainder of 0. Let's check here. Let's check. 8 divided by 2 gives us 0. So this condition has been fulfilled. So that means we go inside the loop. We go inside the loop and we meet another loop. We meet another loop. And what does it say? This one says, while, so that means this one, while means we will continue doing this until this condition is fulfilled. It says, while n divided by p gives you 0, continue doing what is inside, continue doing this. While, so while says, so you see the if is just telling us, the if is telling us that if this is satisfied, enter the loop inside, go inside. If this, and this one was also while. This one was also while. While means we continue doing this as so long as this condition is fulfilled. So long as this condition is fulfilled, we continue maintain being inside that loop. We continue being inside that loop while that condition is satisfied. So while this condition is satisfied, we continue being inside the loop. That's what the while loop means. And this other one is if. This other one is the if. Now, so we've met this condition if. So this condition says if n divided by p gives a remainder of 0, then enter the loop. And then when you enter this loop, you meet a condition that says while p divided by n divided by p gives you 0, do this. What does this mean? What does this mean? This is n divided by p. So what this means, you see what this one means. When we talk of n and then this equals to p, is for instance, when we talk of n, this, and then we write equals, and then if p, what this means is that this n is mutable. This n is mutable, and every time you are replacing it by what you get when you divide n by p. What I mean is this: when I write this, then write 2, what it means that my initial n is 8, but my second n will be 4. So that means you replace what is on the left side by what you get when you divide what is on the left side by what is on the right side. What you replace what is on the left side by what you get when you divide whatever is on the left side by what is on the right side. So that means when I write n is 8, and then if I write this, supposing n was 8, and I write that, what I mean is that this n is changing, of course, and now why I'm getting the word changing is from this while. But if the while was not there, what I mean by n, then this sign b is what I've just written, that n, if it was 8, if I have this, then it will change to 4. N changes to 4. And if it was 4, then it will change to 2. I just divide it by 2. And then n is changing, n is changing. And then again, if I divide by that, then and so on. And so on. So that's what that part means. But now let's understand the part in totality without just without interpreting one bit only. Without interpreting one bit only. What this means is that we will do this. We will do this process until this n divided by p is not 0. Until the remainder of dividing n by b is not 0. We will continue doing this. And that's what you've seen. That's what you've seen. What you've seen is this. When I had 8, and that n was 8, and then it came to 4, and then it came to 2, and then it came to 1 when you divide by 2. So that means our n is now this. So when you check this n and divide by p, which is 2, n divided by, the remainder is not 0. The remainder is not so. So we do that until the remainder is not 0. But while the remainder is still 0, we continue doing that. That's what that part means. I hope you understood. I hope you understood what that means. Of course, if you not, I'll still explain after running the code. And then again, I'll explain with an example. Now let's run the code. Then after running the code, I just show you how the code works using a number. I was using 8. I've not completed, so I choose another number and then show you how this function would be finding the Euler phi of n. Now, this is different. This is the one we had looked at. I want the one we've not looked at. Yes, this one. Now, let me see whether you're seeing what Eve Galole. Can you see? Eve Galole. If Galole is not seeing, what about James Wasonga? Can you see the code?
Yes.
Thank you. What about Kurgat? Kurgat Lians.
Yes, yes.
Can you
Yes,
can
yes.
see? Yeah?
Yes.
And Owen Mawira. Owen, can you see? Owen Mawira. Can you see the code? Owen is not seeing. Okay, but most people are seeing the code. Now, so you can see that this code does not have the GCD function. Of course, we said the GCD function is also important. That is a very easy way of writing it, so that you have the GCD, it does the GCDs, and then this Euler phi function just comes and checks those which have GCD of 1 and then counts. That which has GCD of 1 then counts, and then if the count is 5, it says the Euler phi of 10 of this number is 5. Now, this one does not have that. So it has what I've already explained, but I'll now be explaining with the exact numbers, with the numbers so that you see how it's working. And that one makes it easier now for you to write it. If you can see how it works with the numbers. The number I want to check is this. I want to check if this number, the Euler phi of this number. Let me see if it will give me the results. So that is the number, and we check. We want to see whether it's running. It's running. Good. One good thing with the using big units, the time I've used it, if the code is well written, it will run and give you the result. It will not fail. Of course, it will run. If the number is too huge, it will continue running, even up to tomorrow or the day after. If you just give it time, it will run and give you the result after that period, if the number is too huge. But it will not fail to run. So you can see it has given us a number here. It has given us some number there. Now, so because of time, let's just go straight to how it works so that you see how it works. Whenever you get to know it works, it becomes easier for you even to write it because you understand how it works. So the explanation before I go to the numbers, before I go to the calculations, let's understand the calculations, how it's going to calculate. Now, what it does, that initially it checks if n is 1. And if n is 1, it returns 1 as the answer, that the Euler phi of 1 is 1. That's what it says. That's what the program says. Let's just go back there and see. That's what it says here. That's what it says here. Let me just, it begins by saying if. It says if n is 1, then return 1. Return 1 as the Euler phi of 1. Now, the case when n is not 1, I've already explained that. Let me see what I've written there. I've said when n is not 1, then the result is initialized to n. So that means if n is not 1, then we initially we want to assume that the Euler phi of this n becomes n. But then I've said this is mutable. This is immutable. So that is why we are using n clone, and we're saying that this n clone is used to create a copy of n. So we're using taking a copy of n. That's what n clone means. So it's mutable. This value will be changing from n and so on. Now, if n is not 1, the first thing we say, if n is not 1, the first thing we are saying, let our result, initial result, be n. And then pick a prime number 2, beginning with the 2, the smallest prime number is 2, initialize it at 2. And of course, this is also mutable to be changing. So this is the first prime number. Then let's go back and see what it says. Let's go back here and see. Yes, we've made n our first result. And then we made p to be 2. And this 2 I've said is youth at 2. You see, when you're talking with the big unit, you can also talk of u something. You can talk of u 32, u 128, and so on. And again, that one also gives it more power. When I talk of u 64, again, I'll have given it more power. Or it's still inside something which has more power, and again, you're giving it another more. Now, so after this initial, after making n to be the initial result and making P, the initial P to be 2, you come to the first loop. And it talks about the square of P being less than or equal to n. That's what I've written here. I've said the loop runs while the square of 2 is less than or equal to n. So if the square of 2 is still less than n, you remain inside that loop. You remain inside that loop until the square of 2 is not less than n. Now, after inside that loop, you meet a condition that says if n on division by p is 0, then you enter inside the loop. If n on division, I've just written here short form mod, n mod p, that is, we understand what it means. When you talk of n mod p, we mean n on division by p gives you 0. And that's what we see here. That's what we see here. That is this. That is a short form of this. The short form of this. So I've said, if n on division by p gives you 0, then go inside again. And inside, we have a condition. We have the while, you have the while loop. What does it say? Okay, I've not written that. I think I skipped that. But then it's after, what I've written is now the result, how we update the result. I skipped a lot of things here. Skipped a lot of things because the result is below here. The result is below here. And let me explain what I've skipped. So what I've skipped here, if after the if condition, we go inside, and inside here we say, while this condition is still the way it is, while n on division by p still gives you 0, continue dividing p by this and writing the result that we get. Supposing it was 8 divided by 2, get 4, divided by 2, get 2, divided by, so this is our n. Then n changes again to 4, n changes again to 2, n changes again to 1, and then check here. Check here. Come on, no, we are here. Check here. Check here. If p on division by, if n on division by p gives you 0, so our n is 1. So we want to divide this 1 by 2, and the remainder is not 0. The remainder is not 0. So you now exit. You now exit. When you exit, you come and update the result. Update the result. When you exit this inside loop, you now update the result. How do you update the result? The initial result was n. Our initial result was n. Now, we have written here n minus the result of what is on the right-hand side. N minus n divided by p. So our n, our new result, no, not n, our new result becomes the result which was here. The result, the initial result, divide by, no, not divide by, minus n divided by 2. That is our new result. That's our new result. So the result, the result which we left here, the mutable result which was there, take it, divided by 2, that's what we return, by, and then there's a minus here. So what this, and then subtract from it, whichever is on the right side, and gives you this point. At this point, that is becomes the new result. Now, our first P, we've exited this loop and updated the result. After updating that result, we then say move P plus 1. That means move to the next P. Move to the next P. In fact, this is supposed to be is plus. Okay, I put 1 here. When you put 1, is what it does. If P was 2, it will move to 3. That's okay. But then we need to go up to, we need to continue. So you see, you move to 3 now. When you move to 3, you begin, you come back here. You come back here. You come back here. You see, there's an N you came with. There's this N you got here. The final N we got. Do you remember when I was doing and I got some 1 for that particular case, it's 1. So that now becomes our N here for the next the second working. And then our P now is 3. And then you check 3 times 3 if it's less than or equal to N, 1. There are cases when it will not be 1. There are cases where it will be 1. And then you redo this process with the 3 with the new N. With the 3 with the new N you got here, you redo this process until you exit the loop. When you exit the loop with some N, increment our P again to 5, the next prime number, and then come back here and redo the process, and so on, until N is greater than 1. If you find that N is greater than 1, there are cases where N will be greater than 1, the result will be given by this. The cases where N will be, like you see, like in this case, when I was using 8, our N became 1. The final N after dividing by 2 and so on. Let me just show an example very fast, but I can see it's already time. I want to use that 6. I want to get the value of 536, and I want to use this program. So the first thing, I initialize my result to be 36, and my N, my P to be 2. Then I check whether 2 times 2 is less than or equal to 36. That's why I'm checking. 2 times 2 is less than or equal to 36. And if that is the case, I go inside and see whether 36 divided by 2 gives me 0. That is that condition. And then if 36 divided by 2 is 0, I enter that inside loop and then start dividing 36 by 2 until I get a remainder that is not 0. Until I get that at the end that I have divided by 2 does not give me 0. So that's what I do here. So since that 6 divided by 2 is 0, I divide it to get a new N, which is 18. Then N again, 18 divided by 2 again gives me 0. So I will divide it to give me 9. Then 9 divided by 2 does not give me a remainder of 0. It does not give me a remainder of 0. So I exit that loop. When I exit that loop, my N is 9. My N is 9. Remember the initial result, our initial result was put at that 6, and we say the mutable. So when you exit that loop, what do we have? When you exit that loop, and again, our P that we've been using has been 2. We've been using 2. So we divide until the remainder is not 0. So now, when we exit that loop, what we have, the result we had earlier, our P, which is 2, now using this 2, we can calculate the new result. The new result, I've used the method that you are familiar with, but now the one that we have on our code is this result becomes, the way I've written it as minus, they've written it this way, minus result divided by P. In this case, our P is 2. So the result that I have here is that 6 divided by 2 will be 18. So this means that 6 minus, this is what it means. Result, there's a minus here. Minus, so for me, I used a formula that you're familiar with. But if I was not using that, if I'm using the one of the code, it would be 36 minus equals here, then 36 divided by 2. 36 divided by 2 be 18. 18 from 36 gives our new result, which is 18. So 36 minus equal 36 divided by 2. So in other words, 36 divided by 2, subtract from this 36, and you get 18. So this is our new result now. We now got the second time. This time we increment 2 to the next value. Our P incremented to the next value. The next value is 3. And then check this condition. And this is our N now. 9 is our N. This is the one coming with. This is our N, the one which was after 2. Now check this. Our next P times our next P is less than or equal to 9. So you discover that in fact, this is equal to 9, which is true. So if it's true, proceed inside, go inside. And inside, check whether N divided by P gives you 0. If N divided by P gives you 0, go inside and divide. And divide until this condition is not met. So we go inside and we so our N was 9 divided by 3, get a new N, divided by 3, get another N, and this time we've gotten 3 cannot divide. 3 can exit this loop again. Cannot divide. So loop is not on. Remember our result is at 18. And remember our P is 3. Our P is 3. So it's time to update the result. It's time to update the result. You see, it was mutable. It was mutable. So now update the result. The initial result we have is 18. New result will be given the minus result divided by P. P in this case is 3. So that means our result would be, our result we are coming with is 18 minus 18 divided by 3. 18 divided by 3 is 6. 6 from 18 gives you 12. But of course, at this point, I was using a method you are familiar with, but the method of the code is the one I'm now using so that you understand how the code is working. Now, so our N is what? Our N is 1. We now go increment the 3, P. Increment the 3 to the next P. Increment. So the way I wrote, I just said +1 is okay. So you just do it +1, but you can go to 5, there's no problem. So when you do it +1, then it means P becomes 4. Then check if 4 times 4 is less than or equal to 1. If you find it's not, then you cannot go inside that loop. You cannot go inside. So in fact, what you are finding here, that it's greater than 1. So since it's greater than 1, you don't go inside that loop. So you don't go inside that loop, and then it means the next part does not apply to this. The next part is this. The next part is this. The next part says, if n is greater than 1, if n is greater than 1, if n is greater than 1, then you write the result this way. But in our case, n is not greater than 1. So our result remains as 12, the one we were coming up with. So that remains the result. Now, so I think I can show another example, but not just you look at it because they are recording. So you look at this result, the explanation, so that you can familiarize yourself with this. Now we are increment from 2 to 3, increment, and increment to 5, increment to 7, and go until you exit the loop. That is how you do it. That's okay. So I wish to end there so that we meet tomorrow. Thank you.
Thank you very much.
Alex, an announcement?
Yes. Maybe Simon, you can end the recording.